So now let's come back to the proof of this, that that global freeing of global functions are constants. So first of all, so let's come back to the proof of the proposition. First of all, if you take a constant, then of course they are regular function. There is no doubt, right? And this OI of course it is sitting inside SY 0. Okay, not 0. Okay. Take the quotient field of SY, or let's write one more step. OI, it's a regular function. Of course, they are element in the function field because corresponds to its, what is ky? Ky is u comma f, right? So if u is x comma f, so they are also element of the function field, right? Now this ky, now the point is this ky is sitting inside the quotient field of sy. Because what is ky? Ky is degree 0 part of f by g. So of course it will be in the sy, but this is a bigger field where you are not taking the degree 0 part. So this is a subfield here. Okay, is it clear? This ky is the degree 0 part of so this a quotient field of sy is what? This is nothing but sy of 0, but this is nothing but sy of 0 0, round bracket 0, right? Degree 0 part of the so this is a subring here, subfield here. So now point is that now how will you prove that this is also in K? So how do you prove? So if you take an element, so strategy is that you take an element in OY. So I say that AF is integral over K, or AF is algebraic over K. So if I am able to get a polynomial in Kx such that F satisfies that polynomial. If that is the case, because K is algebraically closed, then F has to be, then there is no choice. F has to be in K, right? Because if you are at a polynomial over an algebraically closed field as roots inside a K. So that is the aim, that I will show that if I take a element F in OY, then this F is algebraic over K or integral over K, right? So that is the strategy. So to show, so claim F is algebraic over K. If I prove this, then I am done. So how do you prove this? So first of all, so you have this OY, and then you have this O. So now because Y is irreducible, I can restrict on YI. Now you see that this is an inclusion. If F and G, if F restricted to YI is same as G restricted to YI, then F has to be equal to G. This we have seen. This is an inclusion. And this OYI, of course, this is in KY, and it is in the quotient field of SY. Okay. So when I think of F, so F going to F restricted to YI. So because this is injective, so everything I think in element of the quotient field of SY, right? So AF I can think as an element of this big field, quotient field of SY. So now now f restricted to yi, this is the element in OYI. So, what does it mean? That means f xi, so f is some g by xi power mi, but degree of g is same as degree of mi, or in other words xi power mi times f is in OYI, which is AYI, right. See, element of OYI are of the form g by xi power mi, but degree of g is same as degree of degree of xi power mi, which is mi. So then, if I multiply by xi power mi times f I am thinking as an element here, then it should be element of AYI. It is g, which is the element of AYI. So this is, so for every I can choose a mi, right. So this you do for every I. Now what you do, this technique, the maximum technique, you take this n to be summation mi, I equal to 0 to n. Or n you can take greater than equal to any n, take any n greater than equal to summation mi. Okay. Now the point is that if you take a monomial, suppose x alpha is a monomial of degree n, then x alpha times f will be always in sy of n. Sy n means the degree n homogeneous elements in sy. Is this clear? Because if you take a monomial of degree n, then it will be something x. So any x alpha, alpha is some indices, right? Alpha naught, alpha n. So x alpha is nothing but x1 power alpha, x naught power alpha naught, x1 power alpha 1, xn power alpha n. Now summation, now x alpha is a monomial of degree n. So that means summation alpha I is equal to n. Now you see, if since n is greater than equal to summation mi, so that means one of these alpha is greater than equal to mi. Right? See, if one of this thing is greater than mi, then x alpha I times f will be in AYI. Which is S of yi. So that will say that this is, so remaining, so what I am saying, so x, so suppose, so what you do, so suppose alpha I is greater than mi or greater than equal to mi. So what you do, xi of alpha I f, you separate it out and then you write the remaining element like x naught alpha naught, xi minus 1, alpha I minus 1, then xi, it is, sorry, here do not write alpha I, you write mi. So xi alpha I minus mi and then x n power alpha n. Right. Now this guy, so now so this will imply that this is s in sy power n, right? Because when you are multiplying by this, then it is going to it is becoming a polynomial, and then again you are multiplying by a monomial, so it remains a polynomial. That is the point, right? So this, see, f has some denominator. So by multiplying by mi, you are killing that denominator. and remainings are polynomial. So that is not a problem, right? So for any monomial of degree n and n is greater than or equal to summation mi, you can do this. Okay. So now, so this implies so this is for any monomial of degree n, now degree capital N. So that means you can do it. So if I take the monomial of capital N, monomial of degree n, so sy n of f is in sy of n, because each it is generated by monomials, right? For every monomial you are doing this. So now you can repeat this process. That is sy n f square. What you do? First you do it on f, and then again you do it over f. So that means this is again in s. So this is sy power n f times f, but again this is nothing but sy of n f. So in general, so this will inside that instead of it is nothing to do with square. So it is true for every f power of f. So what does it mean? For every power of f, see this is a sy power n f q is sub of sy of n. So this imply you take sy. Okay, let's write something. So take the monomial, say x naught power n, which is the element of sy of n. So this implies that x naught power n of f power q belongs to sy of n for every q. Right? You take in particular the monomial x naught power capital N. So this implies sy of f will be inside x naught power minus n sy. Because you take any element x naught power n, so this is same as x naught, same as saying x naught power n times sy of f is in sy, right? So this is x naught power n summation hi fi is equal to summation hi of x naught power n fi, and this guy belongs to a, so now hi is some polynomial in sy, so this is in s of ny. So this will be in, because these are polynomials, so this will be in sy. So now you multiply by x naught power minus n, so this will say that. Okay, so now the something is nice happening. So now they see x naught minus n sy. Sy is a subring of the big quotient field. So now I can think this is in the quotient field of s of y. Here I am inverting x naught power minus n. So this is an element here, right? Okay. So now, so this is as a subring x naught power minus. So this is a subring here, is so, but you see x naught minus n sy is a finitely generated sy module. Generated by a single element, namely x naught power minus n. So, x naught minus n sy is a sub of your quotient field of sy. Of course, this is a sy module, and this is a submodule, but finitely generated by x naught minus power minus n, generated by x naught power minus n. So, now sy, you know this sy, what is this, the polynomial ring sy of polynomial ring f, or f, the ring generated by sy and f. So, this guy is a, this is also a module, sy module. So, this is a submodule of sy x naught minus n, or x naught minus n times sy, which is same. So, sy is a Noetherian ring. So, submodule of this is a finitely generated module. This guy is finitely generated. So, submodule of a finitely generated module is finitely generated. So, since y is since sy is Noetherian, so this is a submodule. Sy of f is finitely generated. But this is everything in the quotient field of sy. Everything is in this quotient field, submodule, right? So, that means what? If something is a finitely generated submodule, means it is the element f is integral over sy. That's the we saw in the commutative algebra. If sum is if you take a element in a bigger ring and take the module generated by that, in the, if a is in this B, and you take some element x in B and consider the polynomial ring, if this is finitely generated, means that x is integral. This is finite. So, these are equivalent condition. Now, you can get a smell of where algebraically closeness will come, but still you have to come down to the base field k. So far, we are over big field, quotient field of sy. So, you have to do little bit more work. So, this implies that f is integral over sy, right. So, that means that you have a polynomial f to the power t plus a1 f power t minus 1 plus dot 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 a naught equal to 0, right, monic polynomial, and these ai's are where? Ai's are in sy. Right. So, now what you do? Now, if you multiply by x naught power n, x naught power n f t plus x naught power n f t minus 1 a1 dot 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 a naught of x naught power n. Now you know the x naught power n f power t, it is in sy of n. Everything is in sy power n. This is in sy n, the degree n. This guy is also in degree sy of n. This guy is also in sy power n. Not power, sorry, the nth degree of sy. Right? So now you take, so now you have a polynomial which is, now you take the degree 0 part, degree n part of this x naught power n f t plus a1 x naught power n f t minus 1 dot 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 a naught of x naught power n. But what is this? This degree n is nothing but degree 0 part of f power t a1 f t minus 1 plus a naught. But what is degree 0 part? So whole thing is 0. So degree 0, degree n part, it should be also 0, right? After all, it is a homogeneous, it's a polynomial. It is in sy, this whole thing after multiplying. So now I am taking degree n part of that. That should be equal to 0. So degree n of this is nothing but degree 0 of this. But degree 0 is nothing but so this is nothing but f power t plus a1 of 0 plus a naught of 0 equal to 0. So degree 0 corresponds to the constants. So that means this is 0. So that means f satisfies a polynomial over k, but k is algebraically closed. So f has to be in k. So f is. So if you remember Liouville's theorem, also it was not so easy to prove. You see that every result which is like a basic result in any subject, does not matter whether you do complex analysis, algebraic geometry or differential geometry. You see these are basic, it's like the subject is depending on these kind of results. They are, to show such a result, it requires some work. The proof. This you will see overall in any mathematics, if you see that some results are very basic, and if you look at in the counterpart, you see that they are also not so easy to prove. If something is not here, maybe a little bit difference will be there, some because of some techniques available, but it's a very useful result. Now you say that so this implies that OY for a projective variety, OYs are constants. So that means what? That means there are no maps to Y to say affine space. Because if there are maps, then you take the projection maps, then there is map Y to A1, but Y to A1 maps are like constants. So if you have a map, so there are no maps from projective to some affine other than constants. So there are no interesting maps, right? Giving a function from Y to n is like giving n regular functions.
And so every constant is regular function?
Every constant is always a regular function. Right? So now, so there are, so as a consequence, there are no consequence. There are no maps from projective varieties, projective to affine. But then what about projective to projective? Of course, there are maps from affine to projective, because we saw, right? Ui, let's take the standard xi not equal to 0. The ui is sitting inside the Pn. So, of course, there are plenty of maps. So, but projective to affine there are no maps. But now you can ask the what about the projective to projective maps? Are there? There are plenty of maps. What about a projective to projective? There are non-constant maps. There are no non-constant. Or non-trivial maps. Projective to projective. And these maps, to define such maps, you need to be, how to classify such maps? It's not easy. You need to introduce more techniques like divisors, line bundles, that will give you a map to. So, projective space, first you understand what is a map from projective variety to projective space. So, giving a map from projective variety to a projective space X to Pn. So, you have to construct what are called line bundles, and then that sections will give you maps to projective space. So, then divisors, ample line bundle, very ample line. The linear system, it is this leads to study of divisors and line bundles and projective varieties. So, these are more advanced topic. Maybe in second course you learn all this. So, this is a motivation to learn something more deep, because you want to understand, like you want to relate two things, right? How do you relate? You relate by whether there is a map or not. That's how you relate two things, right? Whether you can connect one to another. So, to know that whether there exists any such, like here you are saying that this theorem is telling that you cannot compare projective space and affine space. They are completely two different ball game, right? Okay, I'll stop here.